46, and I'm assuming it's section 5.7, correct?
5.7.
Yes, so 536, perfect. So we have, is the one with DP, right? DP over DC.
Yeah, that's the correct problem.
Perfect.
Your camera went off again.
Thank you. See, I haven't touched anything. I'll have to deal with that. Please let me know. Don't let me, because now it's not even giving me a sound notification. Find the profit function. So the profit function is what we are asked to determine. And they say if P equals $10 when C equals 61. As we know, this is a point. C is first, 61, comma, the dependent variable, 10. So this is the initial condition. Now be careful because this C does not mean the C constant, right? So in this case, C is cost and P is profit. So keep that in mind. Okay, perfect. So I look at this differential equation and I see that there is no P here. I don't have to cross multiply. I only have to multiply both sides by DC. So then I have dP over 1 if you want to write it, but you don't need it. Negative 200 divided by C plus 3. Everything to 3/2. And this is DC. Perfect. Now I can integrate C alone on one side, P alone on the other. I integrate the left, I integrate the right. I'm not going to put a constant C. This time I'm going to use the constant as D, not to be confused with the cost. There is no problem here, so something must be there. What function prime is 1? Well, it's P. P prime is 1. Okay, so now negative 200 is outside. I will use a substitution. I will say let U be C plus 3. No problem because du equals dc. So this is 1. When I differentiate with respect to c is 1. So this will be changed into du. The negative 200 is outside. So du at the top. And the denominator will have u to 3/2. Moving on, p equals negative 200. The integral from u to negative 3/2 du. Finally, I'm integrating this. So p equals, and I can say now that not yet because I have to have c. So I'm not going to put the function, the independent variable yet in here. So u to negative 3/2 plus 1 over negative 3/2 plus 1 plus a constant d. I will flip this after I calculate. I will replace u by c plus 3. And I will determine the constant based on the initial condition. Now let's stop for a second and see if you have any questions. So what we did, we separated by simply multiplying by DC. All this piece has numbers, operations, and C alone. This side has only P. I'm ready to integrate both sides. There must be a dP and must be a dC. I cannot integrate if there is no dC. I cannot integrate if there is no dP. So which function prime is 1? Well, P. When we talk about P, right? If I have dx, then I will put x. But I have dP, so I have to put P. Equals. Negative 200 is outside. I realize that C plus 3 will be denoted by U. du equals dc. This will be replaced by du. And this will be replaced by u to 3/2. But u to 3/2 is u, 1 over u to 3/2 is u to negative 3/2. I copy this, I copy this, I copy this. And now I find the antiderivative, which function prime is this, u to negative 3/2 plus 1 over the same number. I don't have to think, I just have to copy, plus, and I cannot forget, remember, we don't put a d1 here and a d2 here, we combine them and put one d on one side. Constant d. Okay, next. Any questions so far? Okay, next. P equals negative 200. Negative 3/2 plus 1 is negative 1/2, and I have to flip it. Negative 2. U, again, the same thing. Negative 3/2 plus 1 is negative 1/2. Negative 1/2 plus a constant d. I have to replace u by c plus 3. I have to multiply these two, and now confidently I'll say this is indeed a function of c only. Because now I replace u by our notation, c plus 3, to negative 1/2 plus a constant d. I can rewrite it because I know what this means. P of c equals 400 over the square root of c plus 3 plus a constant d. We will determine d from the point given to us, 61, 10. Let's see if we have questions here. Any questions? So when I multiply these two, I got 400. This goes to the denominator. This was replaced. It goes to the denominator. It's negative 1/2, which means the square root in the denominator. And now, when c, which is the independent variable, is 61, the profit is 10. Good. So 10 equals 400. 61 plus 3 is 64. The square root of 64 is 8, plus the constant d. 400 divided by 8 is 50. I move 50 to the other side. Let me write it. So then from here, I know that d equals negative 40. I determine the profit. Profit function of the cost is 400 over the square root of cost plus 3 minus 40. And that is part A, I think. Yes. At what cost will the firm break even? This is not calculus. The break even is when the profit of C is 0. So I have to set this equal to 0. 400 over the square root of C plus 3 equals 0. In other words, equals 40. I will cross multiply. So I have 400 equals 40, the square root of c plus 3. Of course, I will divide both sides by 40. So I get 10 equals the square root of c plus 3. What type of equation is this, and how do we solve it?
It's quadratic equation.
So before you identify an equation, you should say this. Give me a second to read it. 10 equals the square root of c plus 3. Read it for a moment and then think. What type of equation is it then? Anyone? Okay, let's read it again. 10 equals the square root of c plus 3. What do you think? Anyone?
Is it rational?
Okay, let's look at this one. 1 divided by x equals 2. What will this be? Of course, not connected to the problem. Here I use the word divide, quotient. This is rational.
Wouldn't x equal 1/2?
Yes, but what type of equation is it?
Radical.
Yes, this one. Yes. Yes. This is a radical equation because I said the square root. This is a rational equation because I said 1 over x. If I say 1/2 equals x, then this is linear. But if I say whatever over x, then it's rational. If I say natural log, then it's natural log. If I say e to x plus 5, then it's exponential. Good. How do we solve a radical equation? What do we need to do with a radical equation to solve for c?
Wouldn't you square both sides?
Excellent. Yes, 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 indeed. That's why we need to be able to identify these equations. Here, rational, cross multiply. Here, I don't cross multiply. This is linear. If I don't have x in the denominator, it cannot be rational. It has to be linear. Good. So we square both sides. Square here, and we get 100 equals c plus 3. Move. So c equals 97. So the profit for this business will be 0 when the cost is 97. Very good. It was a long problem. Yes, I write very, very big. Of course, it's not going to take you 3 pages, 2.5 or whatever. I write big with markers and everything so you can see, so I can also scan this for you. But it was a long problem in which we had a lot of steps, separating, using substitution that we learned in chapter 4, then changing it into 1 over with the square root, then plugging in the initial condition to determine the constant, rewriting the function. So this is part A. And in part B, we were asked, okay, find the cost when the profit is 0. Initially, if you ask me what type of equation this is, I'm going to say it's a combo. It's a combination of a rational with a radical. But once I cross multiply, it becomes a radical equation. Good. Perfect question. Anything else? Did you need anything else from anything? From homework, from my lab math, from anything? Do we need to practice anything else? We will have a review, of course, next week for the test of everything, chapters 4, 5, and 6. Any questions? Okay, then in the last chapter for us is chapter 6. It has 6.1 through 6.4. I would like to start with 6.4 because it will take us 5 minutes or less. But what is the title of the chapter? Functions of several variables. Functions of several variables. Why I'd like to start with this, because I'm not going to ask you to do any work here, only calculator work. Okay. So let me explain what this last section deals with. And the title is it's an application, specific application of functions of several variables. And the application is called the least squares technique. And you can say, how come that this is in here? We did this in statistics with a calculator. It's basically algebra. No, it's not basically algebra. It's basically calculus. But we teach this method in statistics without telling our students how we use calculus to determine the least squares technique. Okay, so let me explain. Let's suppose we have collected data on, I don't know, let's say 10 people. I select 10 of you. I give you numbers. The first person with no names, the first person has number 1, the second number 2. Oops, I meant 10, of course. Let's say I select 10 people, and I measure your height and blood pressure. So this is 1 for the person 1, this is 2 for the person 2, and so on and so forth. Height of the person 10, of course I have to write 3, and blood pressure for the person 10. It means that I have 10 ordered pairs. So I'm going to say the height is on the x-axis, as you see it, as the first variable, and the blood pressure on the y-axis. And let's say I plot these points. Let's say 5'5", 100, 5'7", 110, 6'0", 115. And I plot the points. And these are my points. 2, 4, 6, 10, 9. Okay, 10. Do I have 10? 10, 2, 4, 6, 8, 10. Oh, good. So I plotted all these. And because it has this shape of a line, I'm going to say, can I find a line called of best fit, or even better, the line with the least squares, least error. So obviously the line will not be this. It would not be this. It will be something so that a line that, let's say it's this line, where the errors, this is the one error, this is another, this is another, this is another, this is another error, this is another error, or these squared are minimum error. But every time we talk about minimum or maximum, we talk about calculus. But the formulas are determined for us. This is available in our calculator. So I'm going to skip all the explanation of how we get the formulas to determine the line of best fit. Can I draw another line? Yes. Can I draw another line? Yes. Can I draw another line? But I'm really interested in the one that has minimum error. Okay, and that will be called the least squares, because the errors have to be squared. Least squares regression line. Now, what if I collect the same data and I have this graph? So this was a regression line because it was a line. But what if I have the same data, I am plotting it again here. So this is the height and this is the blood pressure. Notice that all these points are on the same person, right? The first person has these two numbers, the second person, and so on and so forth. So they are paired data. Paired data. Okay? And let's suppose now when I plot my points, the 10 points, I get something like this. I'm plotting more. And you can say, but this is no longer a line. Yes, that's true. This kind of looks like the square, right? A quadratic. Least squares. So it doesn't necessarily have to be a line. And here is one more, and we are going to look at those with a calculator to determine and predict. Okay, so I'll explain in one more second. Just give me one more. Okay, what if I have same thing? I have the height, I have the blood pressure, and let's say this time I get these points. This is what we've been facing for the last 2 years. This function, it made us crazy. But this is exponential. Exponential least squares. So we don't necessarily, we have to look, we collect the data, we plot the data, and we make a decision. What kind of regression am I looking at? Exponential, a quadratic, linear. Okay, so now the question is, why? Why do I care? Okay, I collect the data. I want to see how many people are getting sick with the virus, whatever. I want to see and the model for prediction purposes. For prediction purposes. That's why. We want to be able to predict. So in order to predict, we have to determine this model, like y equals. Here, y equals. This one will be a quadratic, something with x squared. This one may be e to the x plus whatever. And this one will be a line, like y equals 3x plus 1. So the idea is to be able to predict. Now, there is a problem with prediction. What is the potential problem with prediction? Do not go too far out of the data. What does that mean?